We next discuss about the one of the important circuit which is known as the clamper. Okay, we have two types of clamper basically. Okay, the positive clamper and negative clamper. Okay, negative clamper. So what is the application, what is the use of this clamper? Okay, the clamper is a circuit which is used to clamp the voltage at a desired level. Okay, so this is used to clamp the voltage at a desired level. Okay, desired level. So you can see something like this. Suppose for example you have a input like this. Suppose you have an input like this and the reference actually it is 0 here. Okay, and this is v of t. Now the clamping means okay, you are shifting this voltage. Okay, you are shifting this voltage. You see here the reference is actually 0 here. This reference we are shifting to some other point, let's say some voltage vb. Okay, and we have the same waveform with the same shape, but it is clamped to some voltage. Okay, this is known as we are lifting the voltage. Okay, so this kind of clamping is known as actually the positive clamper. That means we are shifting up, so that is known as the positive clamper or positive clamping. Okay, and suppose for the same thing, suppose you are shifting to some other which is some other level which is say maybe minus va, some other level. Okay, then it will be looking like this. It will be like this. Okay, and now you can see the 0 volt is here. Suppose the 0 volt is here and you are shifting the whole voltage waveform to minus va. So this kind of clamping is known as negative clamping. Okay, so this is the clamping actually. So we will see how we can do this operation by using a diode circuit. Okay, so we will first discuss about a circuit which is I will draw the circuit. Okay, we have a circuit diagram like this. You have an input V in. Okay, and I will use a capacitor. And I will use a diode. Okay, I will use a diode and I will take the output from here across the diode. I will connect a load resistance RL and I will take the output from here. Okay, so this is a clamper. So we will see what type of clamper it is. Okay, based on its function. Now you see we have an input. Sorry, I will draw the input first. So we have an input something like this. It can be a square wave, triangular wave, or a sinusoidal wave, anything. So I will draw a sinusoidal wave now. Okay, we have a sinusoidal wave. Let's say this is something like a 10 volt and this is minus 10 volt, 10 and minus 10. It's like this. Okay, so this is a sinusoidal wave and this is the time axis. Okay, time axis, and this is v in of t. Okay, I will represent it as v in of t. So this is a function of time. Now we have a capacitor and we have a diode. Okay, now we will see, you know that this is the positive half cycle. These are all the positive half cycle. Okay, this is positive half cycle and the other one actually it is negative half cycle. Okay, now we will see what will happen during the positive half cycle. During the positive half cycle, you know that this is positive and this is negative. That means your diode is having a p type semiconductor here and n type semiconductor here. You can see this n is connected to the p. That means the diode is reverse biased. Okay, the diode is now reverse biased. Since the diode is reverse biased, no current will be there, so nothing will happen during that first positive half cycle. So this is the first cycle. The diode is reverse biased. Nothing will happen. Okay, so I will extend this first. Okay, this. Okay, so nothing is happening now. Okay, now we will see what will happen if I will extend all these lines, crossing points. for the convenience. Now we will see the output V out. Now during the negative half cycle, you can see here what is there in the negative half cycle. During the negative half cycle, you have negative and positive. Now you can see the positive is connected to the P type semiconductor. That means it is forward bias. Since it is forward bias, you can see a diode drop which is 0.7 here, okay, and there will be a current from positive to negative, will be in this direction like this. So the current will charge the capacitor. So the current will charge the capacitor. So the maximum, the voltage maximum across the capacitor will be V max, okay, or VC max you can say. It is nothing but you are giving 10 volt here, okay, you are giving maximum of 10 volt. So you have a 10 volt, okay, and the 0.7 is dropped across the diode as shown here. So 10 minus 0.7, that will be 9.3. okay, so you will be getting 9.3 volt across the diode like this polarity as shown here in the figure. Okay, the polarity will be like this. So the capacitor charging is happening. So you see here during this cycle, okay, during the first cycle the diode was reverse bias, you see, and the second cycle actually what is happening, the diode is the capacitor is charging, capacitor charges. Okay, now we will see our real output from this point onwards. That means after this point onwards, let's see. Okay, the capacitor charger, actually I will explain from this point onwards basically for the convenience what will happen to the next third cycle. Okay, so this is the third cycle. That means the second cycle, so it is the second cycle, second cycle. During this cycle, what is the situation? You know that again this is positive, that means positive and negative. The diode is reverse biased, so no current through the diode, no current through the diode, because the diode is open circuit. Since the diode is open circuit, I can redraw the figure. Like this. You have a capacitor which is already charged to 9.3 volt, okay, and you have an input Vin of t, and this part is an open circuit because the diode is reverse biased, okay, and you have something like RL here, and you take the output here, V out. Okay, now V out is taken like this. Okay, now we will write the Kirchhoff law. You know that this is plus and minus. We will write the Kirchhoff law around this loop and find what is V out. So I will start from here. I will start from this point, that means this one. So it is minus V in of t, then you know this is plus and minus, so minus 9.3, okay, then it's plus, so plus V out of t, you can say V out of t, this is equal to 0. So V out of t is equal to V in of t plus 9.3 volt. So you see here the V in of t has been shifted up, actually shifted up to 9.3. So we will actually, I will draw here. Okay, there is some problem here, I have no space. Okay, so I will show this one as capacitor charging in the second cycle. Okay, now this has been shifted to 9.3. so we have 9.3 volt, this is 9.3 volt, okay, level, this level is 9.3 volt, and V in I will draw as the same shape. So V in will be like this. Okay, so what will happen when V in, this I cannot draw because we are talking about the third cycle, so V in will be something like this. V in will be like this. So V in is, suppose V in is 10 volt, then you have already 9.3 here, so the total voltage become 10 plus 9.3. so this will be the peak. That means it is nothing but 19.3. so this will go to 19.3 volt. Okay, I hope this is clear to you. Similarly, in the next cycle, again in the third cycle, you can say in the in the negative cycle. So this negative cycle, during the negative cycle, in the negative cycle, what will happen, you know that the maximum voltage is minus 10, so minus 10 plus 9.3, okay, that will be the minimum voltage. Okay, the minimum voltage will be minus 10 plus 9.3. What is that? It is nothing but minus 0.7 volt. Okay, so this will go to minus 0.7. okay, so it will be like this. Now again the same thing is repeating, so again it will go to 19.3 volt, and this will go to minus 0.7. So the basically you should know in which direction the capacitor is charging. So you can see that the whole waveform has been shifted up. So the waveform has been shifted up. Okay, so this waveform has been shifted up. Okay, so that is why this is known as the positive clamper. So I will put the heading for this as positive clamper. Okay, positive clamper. I hope this is clear to you. So I will explain you briefly again. So we have a capacitor, as I told you, and we have a power supply V in of T, and we have a diode. Okay, this is nothing but the positive clamper, and we have a load resistance which is RL. Okay, and we will take the output across the load resistance RL. Now you can see here, this is during the first positive half cycle, your diode will be actually reverse biased. Okay, we have something like this as the input V in of T. So during the first positive half cycle, the diode is reverse bias. So that means during plus minus, you can see this is connected to the P, so the diode is reverse bias. Okay, so nothing, forget about this thing. Okay, next, during the negative half cycle, what will happen? This is negative and this is positive. Now positive is connected to the P, so the diode is forward bias. So the current will flow like this, and there will be a voltage drop across the diode is 0.7 during this cycle. Okay, so since you are giving, suppose this is 10 volt and minus 10 volt, since you are giving minus 10 volt, that means this is 10 volt like this with minus and plus, your capacitor will charge to 9.3 in this direction. So plus minus 9.3 volt, it will be like this. Now during the next cycle, that means during the next positive half cycle, I am showing with the blue color, that means this will be positive and this will be negative. Your diode will be reverse biased. Because you are connecting the negative with the diode, the P of the diode. So the diode will be again reverse bias. That means you can draw the circuit from now on. You can draw the circuit like this. This is open circuit, and this like this. This is your RL. Okay, V out. So it is something like this. Okay, now what we have to do with this, you see here it is open circuit and you have a voltage across the diode as 9.3 volt, and this is your V in of T. So you can say that your total voltage output is nothing but V in of T plus 9.3 volt. Okay, so this is your V out. So you can see here that from this cycle onwards, you can see that the entire voltage has been shifted to 9.3 because you have a plus 9.3. You see here it is plus 9.3. So it has been shifted up. Okay, it has been shifted up like this, and this will be going down, shifted up and going down. So it is 19.3 here, 10 plus 9.3, and this is minus 0.7. So this will continue. Okay, so this is the positive clamper. Since it is shifting up, okay, it is shifting up, we will call it as a positive clamper. Okay, positive clamper. So I hope it is clear. Next we will discuss about the negative clamper. Negative clamper. negative clamper, actually it will be something like this. I will just change the direction of the diode. Okay, you have a diode like this, so I will use a electrolytic capacitor, something like this, and this is V in of T. So I will use a diode like this. Okay, I will use the diode like this, and this is your RL. Okay, I hope this is clear to you. Now we will have an input, something like a triangular wave. Anything, you can have any kind of input like this, triangular wave or sine wave. So let's say this is 10 volt and this is minus 10 volt, 10 volt and minus 10 volt, like this. Okay, so this is your V in of T. Now we will see what will happen during the positive and negative half cycle. Okay, now you can see here that during the positive half cycle, we have positive half cycle like this. First positive half cycle, you can see here the diode negative is connected to the n-type semiconductor, and this positive is connected to the p-type semiconductor, so it is forward bias. So definitely the current will be flowing in this direction. Okay, so it will charge the capacitor. So we will see that there is a voltage drop because of the current. So 0.7 will be the voltage drop across the diode. So since you are giving a maximum of 10 volt, the voltage drop across the diode is 0.7, and the voltage drop across the diode is 0.7. The capacitor will be charging to a maximum of 9.3, because 10 minus 0.7 is 9.3 volt. Okay, so but the polarity will be like this, not like in the previous circuit. So the polarity is just reversed here. Now you see what is the output. We will see what is the output. Okay, we will see what is the output. So before that I will draw the lines. This is okay. Now you see this is V in, and I am taking the output from V out here. So I will write the Kirchhoff law. You see here this is minus, so minus V in of T, then again this is plus, so plus 9.3, then again plus V out of T, this is equal to 0. So V out of T is nothing but V in of T minus 9.3. so that's it. Okay, so you can see here there is a minus 9.3, so our reference has been changed to minus 9.3 here. So you can see our reference has been now changed to minus 9.3. that means it is shifting down. That's why it is known as negative clamper, as I told. So it is shifting down. Now when the input voltage, you see here, when the input voltage, so first cycle, forget about the first cycle, because first cycle actually representing charging the capacitor, okay. Now in the second cycle the input is minus 10. When the input is minus 10 minus 9.3, you will get the output as minus 19.3. so this guy actually it will go to minus 19.3, okay, minus 19.3. and you can see here when the input is 10 volt, then 10 minus 9.3, because this is showing the input. Okay, so it becomes 0.7, so it will go to 0.7. okay, my drawing is not perfect, that's why. So it's go to 0.7 maximum, then it will go down again to minus 19.3, minus 19.3, then it will go to 0.7 again, it will be repeating. So this is the circuit, actually this is the output. So you can see that it is shifting down, so it is known as the negative clamper. Okay, negative clamper. It was this kind of circuits was very common in our old television to clamp the different signals which is related to the primary colors of the color television, okay, to different levels. Okay, so that was one of the application. So we will see, so this is the clamping circuit. So we will do some revision before the exam. So this is we are going to revise some of the problems. let us assume that you have a diode circuit, something like this. This is 12 volt, okay. This is 1 kilo ohm, and this is a diode, and there is 1 kilo ohm, okay. Next you have a diode like this, D1, D2, this is D1, another one is D2, okay. And you have 1 kilo ohm resistance here again, okay. You have another diode which is connected like this, okay, and another diode which is connected like this, okay. So not this, there is no connection here, and this is 1 kilo ohm, okay. And there is another diode here which is D3, okay. This is connected here like this, and this is D4, and this is D5, okay. And from here there is a 1 kilo ohm resistance, and this is your D6, okay, and it is going to the negative terminal of the battery, okay. Now I will mark some currents. You can see this is I1, okay, and this current is I2, and this current is I3, okay, and this is I4, okay, and this is I5, and this is I6, okay, and okay, that's it. So assuming, the question is assuming the practical model for the diode obtain I1, I2, I3, I4, I5 and I6, okay. So this is the question, how to obtain all the current, okay. So we will first the solution to this problem, we will see which diode is on and which diode is off, okay. You can see here that the diode which is D5, you can see here the diode D5 is connected like this. You can see here the diode D5 is in off state basically, because the negative of the battery is connected to the p-type semiconductor. So diode D5 is off state, in off state. And what about D3? We can see here D3, we will see what about D3 anyway. And you see here that D4 is connected in parallel. D4 is connected as shown here, okay. D4 is connected as shown here, you can see here, this is the connection for D4. The problem is that if D4 is on, then the voltage drop across D4 will be, the voltage drop across D4 will be nothing but 0.7, okay. So the voltage drop across D4 will be 0.7. that means that you are giving plus 0.7 across these 2 points. Let's say this is A and this is B, okay. That means your D3 is also in the off state, okay. And else also you can see that your D5 is off. Since D5 is off, there is no current through D3, so D3 is also in the off state. So now we will see which diodes are all in on state. What are all the diodes in on state? D1 is in on state, D2 is in on state, D6 is in on state, and what about D4? Yes, D4 is also in on state, okay. So since you know that since D5, since you know that the D5, since D5 and D3 is off, we have the current I5 will be equal to 0 ampere, okay. Now you can see easily from the circuit diagram that this current is 0 ampere, since it is 0 ampere, your I4 will be same as that of I6. So I4 will be same as that of I6. Okay, so I think that is clear to you. Now we will redraw the circuit with these notions. Okay, you have a 12 volt and what is that? Yeah, 1 kilo ohm resistance, 1 kilo ohm resistance, and here 1 kilo ohm. That's it. Okay, next there is a diode D2. This is D1 and D2, like this, D2. Then you have D4. This is open circuit because there is no current here, I told you. Next 1 kilo and D6. Okay, so 1 kilo ohm and D6. Okay, this is D6. So that's it. Now we want to find the currents like I1, I2, I3. So we have the current I1, I2 and I3. Okay, and this is I4, and same thing is I6. And also we got that this is open circuit. Okay, this is part is open circuit. So I4 is equal to I6 and I5 is equal to 0. That we got it. Now you know that what will be I2? The voltage drop across D2 will be nothing but, because D2 is on, the voltage drop is 0.7. So this voltage drop is 0.7. So the above across the resistance, the voltage is again 0.7 volt. So I2 will be nothing but 0.7 divided by, you have 1 kilo ohm, so it is nothing but 0.7 milliampere. Okay, so we got I2. Okay, now we have the voltage drop across this again is 0.7. Okay, now we can I think we can write the Kirchhoff law around this loop. We can write the Kirchhoff law around this loop. So this is minus, this is plus, this is plus, this is minus, and this is plus and minus, and the voltage drop is 0.7, and this is plus minus 0.7, again plus minus 0.7. Okay, this is plus minus. Okay, like this. So I can say that I will start from here to minus 12 volt. So minus 12 volt plus I1 into 1 kilo ohm. Okay, then again here it is plus minus 0.7 volt. So plus 0.7 volt. Okay, again you can see here again plus 0.7 volt. Again you can see here plus 0.7 volt. Then you can see this part as plus your I1. Okay, I1, because this current is I1, so this current is also I1, and so this current, the same current, it is I1. Okay, so you can see here this is I1. Okay, so I1 is I1 into 1 kilo, then plus 0.7 is equal to 0. Okay, so if you solve this equation, you can find I1 as 9.2 volt divided by something like 2 kilo ohm. Okay, so you can get easily by solving this equation, you will get it as 4.6 milliampere. But you know that your I1 is same as I4. So I1 is equal to I4, but I4 is equal to I6. Okay, so everything is nothing but 4.6 milliampere. And you know that your I2 is 0.7 milliampere. So I3 is nothing but, you have I1 as the total current, I1 minus I2. So this is nothing but 4.6 milliampere minus 0.7 milliampere, which is nothing but 3.9 milliampere. Okay, so I think we got all the currents. So we have I4 and I6, and we got I1, I4, I6, everything, and I2 and I3 also. Okay, we got all the current. So this is how to solve the problem by using the practical model. So we have used the practical model for solving the problem. I hope this is clear to you. Next we have one more circuit like this. Okay, this is problem 1. Okay, we will see another problem. We have another circuit which is having a power supply of 10 volt DC like this, and this is 50 ohm. Okay, and again this is 50 ohm. Next we have D1 like this. Okay, and D3, sorry, this is D2, this is D1. Okay, now this is connected here. Okay, and this is connected with a resistance of 1 kilo ohm. Okay, and you have another connection which is a 50 ohm connection. Okay, and it is connected from here through a diode. Yes, so D1, D2 and D3. So there are 3 diodes. So we will see which diodes are in on state and which are in off state. Okay, so you can see here the positive of the battery is connected here. The positive of the battery is connected to the p-type semiconductor. So the diode D1 is in on state and D2 is in on state. Now you can see here this negative is connected to the p of D3. So D3 is in off state. Since D3 is off state, okay, there is no current through that. So let us assume that this current is I1. Okay, this is I2, and this current is I3, and this current is I4. So okay, you want to obtain I1, I2, I3 and I4 by assuming the practical model. So we are assuming the practical model and we are going to find the current. So the answer, we have seen already these diodes are in D1, D2. So D1 and D2 are in on state and D3 is off. Since D3 is off, let's say this current is I5. I5 will be equal to 0. So you can actually remove the lower part of the circuit. Now since D2 is on, the voltage across this point A and B, let's say this is A and B, that means VAB is 0.7. so I4 will be nothing but this voltage is also now 0.7 volt. So I4 is nothing but 0.7 divided by 1 kilo. It is nothing but 0.7 milliampere. I hope this is clear to you. Okay. Now we have no idea about I3. Okay, we have no idea about I3. How to obtain the I3? So before that, actually you know that this is on. Since this diode is on, this is voltage is 0.7 and this is on, D1 is on, so this is also 0.7. so the voltage between the point C and D, that means the voltage between C and D is nothing but 0.7 plus 0.7, which is nothing but 1.4 volt. Okay, it is 1.4 volt. Is it clear? So it is only 1.4 volt. Now we will see here what is the current I2. So I2 is nothing but, this is VCD. You know the voltage between C and D is 1.4 VCD by 50 ohms. So it is nothing but 1.4 volt divided by 50 ohms, which is nothing but 28 milliampere. Okay, 28 milliampere. So you are getting I2 as 28 milliampere. Okay. Now what will be I1? So we will find what is I1 now. You know that this voltage, okay, yes. Now you see here how to find I1. What is the idea to find I1? I1 will be equal to, you know that this voltage is 1.4. So this voltage is 1.4 volt. So the I1 will be equal to, you have 10 volt here, this is 10 volt here, so 10 volt minus 1.4 divided by 50 ohms. Okay, because if you know this voltage, let's say this is P and this is VC or VCD, so I1 can be obtained by Vp minus I1 can be obtained by, you have Vp, so Vp minus VCD. Okay, so this is Vp and this is the point, let's say this is P and this is Q, so you can say this VPQ minus VCD divided by the resistance is 50 ohms. That means you have 10 volt, VPQ is 10 volt and VCD is 1.4 volt as you have obtained while calculating I2. So you will get this as 8.6 divided by 50, it is nothing but 172 milliampere. Okay, so you got what is I1, you know what is I1 and you know what is I2, then easily you can get the, and you know I3. Okay, you know I3, sorry, you don't have any idea about I3, but you know I4, so you can find I4 easily. Okay, so you know I1 is equal to 172 milliampere and I2 is equal to 28 milliampere. So you can see here, I will redraw this part of the circuit. I think this is your I1. Okay, this is your 10 volt and you know this part of the current, what is that I2, so this is 28 milliampere and this current is 172 milliampere. So easily you can find this current, how much this is this current. So this current will be 172 minus 28, which is nothing but 144 milliampere. So you got this current. Now it is going into two branches, you can see here, one is going through this diode, okay, as we have seen this diode, and another part is you see here, it is going through a diode D2 and it is going through a resistance. Okay, and through the resistance you have the current I4, already you have found it. So through the resistance the I4 is nothing but 0.7 milliampere. So what will be the current through the diode? So this current will be nothing but, so this current will be nothing but, this current is nothing but 144 milliampere minus this current, you know it is 0.7, so minus 0.7 milliampere. So this is nothing but 143.3 milliampere. So that will be the current, what is the name for this current? It is I3. So that will be the current I3. So I3 will be equal to 143.3 milliampere. So we got I1, I2, I3 and we also got I4. Okay, so that's, and I5 is already 0, so we got all the currents. Okay, so this is how to solve this kind of problem by assuming the practical model. So usually for the exam I will be I will be giving you the problem according to the practical model only. Okay, so it will be convenient for you to solve this type of problems. So that's it. Now we will see another problem which is related to the half wave rectifier, sorry, full wave rectifier. Okay, you have a full wave rectifier which is having a voltage supply of 230 volt RMS. Okay, 230 volt RMS, and this is the transformer, and you have a ground here. Okay, and this is the voltage between the ground and the center tap. And you can see here this is a 100 ohm load which is RL, okay, and you have the diodes like this and this. Now you will take the output between this and the ground, okay. So this is your output, this is your output, okay. So it is asked to find a lot of things, okay. So the first part, actually the frequency is also given. The frequency input was 50 Hertz. So the first part of the problem is to obtain the output frequency, okay, frequency. The second part of the problem is to obtain the peak voltage Vm, okay, and the turns ratio is given. I forgot to write it, is 5:1. And the C, the third part of the question, maximum output voltage, okay, maximum output voltage. And the fourth part of the question is the average output voltage, okay. And the fifth part of the question is the peak inverse voltage, okay. So we will solve one by one. So the first part is the output frequency. Since we are talking about the full wave rectifier, so we know that the output frequency will be equal to 2 times the input frequency. It is nothing but 2 into 50 Hertz, okay. So you will get the output frequency as 100 Hertz. So I hope this is clear to you, because the full wave rectifier output will be something like this, okay. So the time period has been reduced to half, that's why the frequency is doubled, okay. This we have already discussed while discussing okay, while discussing the full wave rectifier. Now we will find what is the secondary voltage in total. So this secondary voltage V secondary, so V secondary, first of all we know that it is 230 volt is RMS. We will first convert into the maximum, okay. After that we will multiply with the turns ratio 1 by 5, okay, 1 by 5. So this is V secondary. Now you know that Vm, this is the maximum V secondary, okay, V secondary max or maximum or peak, Vp secondary, you can say here Vp secondary, that's better, Vp secondary. So this is Vp secondary. So Vm is nothing but Vp secondary by 2. So this is nothing but 230 the square root of 2 into 1 by 5. Now you are dividing everything by 2, so you will get this answer as 32.52 volt, okay. So this is now the maximum output voltage Vp out. You can easily find it. You know Vm, because since only one diode is on at a time, so it will consume, actually it will take 0.7 volt. So the output maximum will be the remaining voltage. So Vm minus 0.7, it is 32.52 minus 0.7, which is equal to 31.82 volt, okay. Now we will see what is the average output voltage. So the average output voltage is 2 times Vp out. So V average, I will, for a full wave rectification, is nothing but V average is nothing but 2 into Vp out divided by pi, which is equal to 2 into 31.82 divided by pi, which is equal to 20.26 volt. And the peak inverse voltage is 2 times Vp out plus 0.7 is the peak inverse voltage. So you will get it as 64.34 volt, okay. So this is how to solve this kind of problem. I hope this is clear to you, okay. Next we will see another problem which is we will see another problem which is a half wave rectifier with a filter. Okay. So half wave rectifier with a filter. Now you have a transformer, okay, and you are giving 230 volt VRMS with a frequency which is 60 hertz, okay, and this is the secondary of the transformer, and the turns ratio is 10:2, and you have a diode here, okay. This is half wave rectifier. Now you have a load resistance RL which is equal to 2 kilo ohm, okay. But you have one more thing, it is there is a capacitor C which is equal to 50 microfarad, okay. Now there are 4 parts in the question. It is asked to find out first what is Vp out, okay, then that means the maximum output, the maximum current If maximum, that means this is the current If, we want to find the maximum current. Next the ripple factor, okay, then the peak inverse voltage, So we will solve this problem, all this part one by one. You know that the peak inverse voltage is let me check 1 second. So we have the RMS voltage 230 volt. So first of all we will convert it into the peak voltage by multiplying with the square root of 2. After that we will multiply with the turns ratio 2/10, then we will get the Vp secondary, okay. So we will get the Vp secondary, okay. So this is, so Vp secondary is nothing but this one. So Vp out can be obtained by Vp secondary minus 0.7. So you will get this as you have 230 into square root of 2 into 2/10. So this, the whole thing minus 0.7, you will get it as 64.35 volt, okay. So you got the maximum voltage because one diode will be on at a time, so it will take 0.7, so the remaining voltage will be the maximum output, okay. So I of max means Vp out divided by your RL. So you will get it as 64.35 divided by 2 kilo ohm. So you will get the current as 32.175 milliampere. So this will be the current. Now the ripple factor is nothing but VRPP divided by VDC. You have to multiply with 100 to have the percentage. So first of all we will see what is VRPP. VRPP is nothing but 1 by F into RL into C. Since this is the output F, but you know that output F is not same as that of the input F, which is 60 hertz, because it is an half wave rectifier, that's why, okay. So into Vp out, okay, this you will get it as 1 by 60 into 2 kilo into 50 microfarad into 64.35. So this is equal to 10.725 volt, okay, that's it. Next you will get a VDC, okay, so VDC, which is equal to 1 minus 1 by 2 F into RL into C into Vp out, which is equal to 58.987, okay. You will get this thing, okay. You know F is 60, you know RL, you know C, everything, so it's easy to obtain, okay. So the ripple factor can be calculated. Ripple factor is usually represented by R. So ripple factor is 10.725 volt divided by 58.987 into 100, which is nothing but 18.17 percentage. So this is the ripple factor for this. So the last part of the question is the peak inverse voltage. The peak inverse voltage for this half wave rectifier, we have already seen in the theory session that it is nothing but Vp secondary, and you know what is Vp secondary. Vp secondary is nothing but 65.05 volt. Okay, Vp secondary can be easily obtained by using this. Okay, so 65.05 volt. I hope all the problems are clear to you.